So my name is Stephen Restaino. I'm from the University of Maryland. Today I'm going to talk about Raman spectroscopy sensors that we fabricate on paper using a simple and scalable technique using off-the-shelf inkjet printers. And we are developing these for various portable biomolecular assays. So I'm going to go, in case you didn't notice, this is pretty different from what the rest of the session, so I'm going to go over kind of a broad overview and some of the applications that we have with this, in addition to the microRNA sensor that we're developing. I'll get to at the end. So for anybody that that isn't familiar with SERS, it's based on the phenomenon of Raman scattering, which is based on inelastic scattering. So incident light on a molecule is absorbed, and then for various structures, you get excitation to a virtual state, which allows some absorption, and then you get a red shift, and you get a fingerprint of that molecule. So normally this is a very rare phenomenon, so it's very difficult to do. You need very pure substances, but it's been known for a long time that you can actually enhance this over Rayleigh scattering by using noble metal nanostructures on the nanoscale. So SERS has some advantages over a lot of different techniques in that, because it provides a fingerprint of whatever molecule you're interested in, it's label-free, which is important for bioassays. It's very sensitive, and it can be done with the same sensitivity with more traditional methods like fluorescence. It's inherently multiplexible because you get that fingerprint, and you can distinguish multiple different molecules at the same time. And as technologies have improved, these Raman spectrometers have become increasingly portable, where they're not only small, but they're actually handheld and can run off of simple power supplies such as batteries. Unfortunately, most of these are really designed for just doing Raman scattering. They're not really designed for SERS, because SERS devices were traditionally very difficult to fabricate. They were very expensive because they required micro and nano manufacturing techniques in a sterile environment. And to use these very rigid structures, you couldn't do a whole lot with them. In biological assays, you have a lot of preparation and purification for the sample itself, let alone any procedures that you need to do to get that sample onto a simple planar substrate and in a pure enough form to actually detect. So what we have decided to do is, and other groups have done this as well, is basically take these noble metal nanostructures that you can get this Raman enhancement with and apply it to a flexible substrate that allows some fluidic handling like paper. And there are various different fabrication techniques, but our group has pioneered the use of inkjet printers, which allows not just rapid and on-demand production, but actual scalable production, so you can produce as many of these as you want on demand. Like I said, the use of paper provides a series of advantages over the traditional Raman SERS rigid structures. So some of those are the ability to just directly collect your sample. Because paper is flexible, you can take it and you can swab it along a dry surface and collect whatever analytes are there. And for liquid samples, you can simply just take your sensor and dip it into a sample. Some of that can wick up, or you can just detect it directly if you dip the functional end in. You can also purify samples using the chromatographic properties of paper. If you have any sort of balance between your mobile phase and the affinity for the substrate, you can actually separate small molecules or even larger molecules from a complex sample. And then once you have your molecule of interest purified away from some of those contaminants, you can actually then concentrate it and improve your detection limits significantly. So what really motivates us is the ability to do biosense. We really want to be able to take these types of sensors and bring them to the developing world or to a patient bedside and be able to detect disease states or any toxins that may harm a patient. And so when we started with this technique, one of the first applications we wanted to do was to be able to pull toxic chemicals from these complex biological fluids. So we started with milk, and one of the applications that we did was pulling melamine from infant formula, which was a big problem in China a few years ago, led to deaths and I think like hundreds of thousands of people hurt. And so we were able to do this by, like I said before, using chromatographic separation on paper. And basically, we can just inkjet print a large surface area, apply a very complex sample to a particular membrane type, and then use a mobile phase to separate those. And then what we can see here is that if you know ahead of time the location or how far your particular molecule of interest is going to travel, you can actually improve your detection limit by multiple orders of magnitude. So we took, so moving forward, we wanted to, again, like I said, bring this to the bedside. So now we want to do not just milk, detecting toxins in milk, but how about drugs in whole blood? So here we've started with that, doing therapeutic drug monitoring in whole serum. And we've improved on the previous method by making it only a single step, basically taking the wicking properties of paper and doing a vertical flow separation through filtering membranes. And in this case, we are detecting the antifungal drug flucytosine, which has a very narrow therapeutic window and is bookended by non-therapeutic doses, but very closely by a toxic dose. So it's very important for a physician to be able to know throughout the course of treatment what the blood concentration is, and this allows you to do that rapidly and cheaply. And so we were able to detect this drug throughout the therapeutic range in whole serum, which has not really been done before with SERS. So if we want to really get into disease states and not just small molecule drugs, we need to be able to detect macromolecular targets, more traditional disease state analytes like proteins and DNA. But usually if you're going to try to detect these with SERS and even most other techniques, you need significant purification in order to do it, especially with Raman. When you get into these macromolecular polymers that have a very small library of subunits, you really need either a very pure sample or controlled orientation during the deposition in order to get a unique fingerprint from other molecules. So most often what's done are either labeled assays or amplification steps that you then pre and post process in order to get them into get any sort of Raman labeling dye onto your target. So what has been done are simple sandwich assays, which is very similar to the ELISA format for both proteins and nucleic acids. And we've done some work multiplexing polymerase chain reaction as a post-processing step in order to distinguish not just one, but multiple targets, DNA targets from each other. But what we really like to be able to do is turn all of these multi-step, highly technical processes into a rapid one-step assay. And in order to do that, we've designed a competitive displacement assay that can be put onto a single piece of paper along with our inkjet-printed SERS regions. And then in the presence of our target paper fluidics, we'll just wick a nucleic acid reporter from a probe, and then we can detect that in a rapid manner. So we've done this already with microfluidics, but microfluidics is very rarely translated in terms of portable assays. So if we really want this to get out into a patient bedside, we need to make it. We need to really get into a more accessible substrate like paper. So this is the lateral flow assay that we've designed, where we can inkjet print the displacement assay itself, because it's also done on these noble metal nanostructures. We're using gold nanospheres and silver nanospheres for the detection. And what this allows us to do is have a single fully inkjet printed system for the detection of not just small molecules, but DNA and proteins as well. And so we're targeting microRNA with that. MicroRNA, for anybody that doesn't know, is it's an RNA sequence, usually short 25 nucleotide sequences that allow you to have some idea of cell activation states. And so these are indicative of not just disease states, but healthy states. and they can be used for diagnosis of a variety of conditions, including cancer, viruses, heart disease. So they're relevant not just here, but in the developing world as well. But what's really important about microRNAs is they're really not useful as a single biomarker. You really need a panel of them in order to diagnose a disease state. And so you need a method that's inherently multiplexible, which isn't really, is not trivial when it comes to traditional lateral flow assays or ELISAs and PCR. So some of the methods that we've been doing to develop this, first, we need to make sure that we can take these nucleic acid probes, functionalize them with these dyes, and then detect them in our paper-based assay, because we're moving away from these from these small molecules into charged biopolymers once they're attached to these DNA sequences. And what we've shown is that we can detect them reliably, but they require various treatments to the sensor itself in order to get significant binding. And each dye has a particular preference for a particular type of treatment, whether it's acid or a polyamine compound. But we were able to combine these treatments in a way that we were able to detect both. But what can happen as you deposit these nucleic acids is that you don't have, you have way more cellulose or whatever the fiber is that your surface area there. So you really need to make sure that you can get deposition of your probe onto the nanoparticles themselves. So what we've been able to do is promote that binding through application of surfactants that allow concentration of those probes onto the nanoparticles themselves, and we get an improvement in signal. And obviously that's an issue for lateral flow as well, and so what we've shown is that a similar treatment can promote transfer of those nucleic acids throughout the paper. And we've also validated our displacement assay with both DNA and proteins, and so we know that it works, and now the final steps are just to print these onto our single sensor and run our assay, and hopefully no big deal. So thanks everybody for listening, and I'll take any questions.